And let's continue doing these tutorials here. So going into tutorials, gravity pack. This is what we were working on before. Notice it's in its own directory. We keep everything related to a particular model in its own directory. We have a project file. I typically like to give it the same name as the directory. And then we're going to have these data files, which are the scripts. And then we're going to have, along the way, we're going to create the state of the system. So I'm going to go and double click on the project file. And we hooked that up last week so that when you double click, it opens up the PFC2D executable. So I'm going to go back. I've learned how to make the left bigger so that you can see it better. You have to hold the key and roll. There's like a roller thing between your fingers on the mouse, and so that controls the size of that. This thing down here can be controlled also from tools, options. I think it's tools, options, console. They call that the console. Somewhere in here, there's a select font, right? So I can make that thing bigger. And now it's even bigger. So it should be easier for you guys to see what's going on. Okay. So gravity packing, let's review this again. Let's just first run it and look at it. Here's the plot item. These are the force chains. These are the particles. What do you see about these force chains? What's kind of weird about this packing? What do you think? Like, what's the difference between? Come on, somebody jump in. What's the difference here? The pattern that I see.
It's uniform?
Yeah, it's
Sort
like
of.
all perfectly. Sorry, go ahead.
Yeah, I'm just saying it's sort of uniform, so I would say it's the densest state.
Oh, that's an interesting point. Um, I think it is. Yes, if you have, and this is because these are all exactly the same size. And so if you want to pack disks of the same size, this is the packing arrangement that you would want to have. And this is basically what the system is sort of naturally trying to achieve. Like if we run this again with changing the size distribution, or wait, first, yeah, and there's also zero friction here. If we change the size distribution, so we go from 0.03 to 0.05 and make 20 of them. Now you're going to see it's not able to sort of, it's going to be heterogeneous now. And it's interesting because that crystalline structure that you saw before it behaves like a lattice. It actually behaves like a lattice of atoms. And so it's going to have very anisotropic properties. If this was supposed to be a geomaterial, you want to have some kind of heterogeneity like this. You don't want it to be a crystalline arrangement like that. Okay. So the key thing here, again, remember what we did. We're always going to have these same first lines pretty much, right? Model new, create a new model. We always have to, almost always are running with large strain true. What's this random thing all about? Somebody. Who should I pick on? Bowen, what's this random thing all about? Model random.
It sets a random seed
Correct?
to control the position of ball generate position and some other things.
Correct. And why? And so, does anyone else want to add anything to that? Why do we care?
Because we
because
want to. Okay,
Okay, go ahead. Okay,
No, you
because
go
we
ahead.
want to get the same results after each run.
Correct. So again, this is what we call the random seed there's a algorithm, random number generator. You give it a seed and it will give you an infinite sequence of numbers, and that sequence of numbers will be random. And so that's what we use. We take those one at a time out of that list, and we use that when we're generating random positions of particles here. And so because of the magic of computers, if we run it with the same list, we're going to get the same exact status each time of the final configuration, right? So that's what we sometimes want that but also it's a nice thing because if we want to get do a study, for example, of how much variability is going to be produced by changing the packing, we simply need to change this number and we'll get a different configuration, right? Because that initial particle cloud will be different. And that will have an effect. We're never going to get identical results unless we have an identical configuration. Okay. Here we're giving a title. That's useful because we can make it come up here. The way it comes up here is you have to go into, I'm trying to remember here, this checkbox, which is view settings, and in there, oh, we lost Yoon King. Okay, let's see. Go into the view settings, and here you can give the title if you wanted to. So if I say Fred, and if I refresh the screen, it should say Fred, and it's not. What's going on here? Oh, okay. It's because I changed the plot title, not the job title. If I click on this, now it's going to also put a title just for this plot. So you can, say this is the plot of the balls or something like that, and then you can have different plots that are going to show different things. All right, let's turn that plot title off to keep it simpler. Okay. What's this thing about domain?
So basically our workspace size, we're setting the size that we want to work inside.
Correct. We're setting a region in 3D space, and all of anything that's happening in the model needs to be in that region. And we want to make that region, relatively small. The reason we do this is so that we can make that cell space adaptively make itself recursively smaller as needed just where the particles are. And if you have an enormous domain, then you have to have an enormous cell space, even though all your action is only happening in one small area. So that's the reason. Turn that off. Go back to this. What else we got going on here? What the heck is this business here? Contact CMAT. What's the CMAT? Stands for Contact Model Assignment Table. Ling, we haven't heard from you. Can you tell us what is the CMAT?
I can hear, yes.
I'm sorry? Oh, do you remember or not?
Yeah, I remember.
So what is the CMAT?
Give the model a contact.
Mm-hmm. And what about the contact? So did you just talk about this here? It gives the model a contact, or tells it who can help them out. Shihang.
Okay, the CMAT is a table. We have it records all the different maybe all contacts property, and we can apply the detailed property of each kind of contact through this CMAT, and the default model. Okay. Also, we can divide it by type, like ball contact and ball facet contact, and also we can use the by default to set all the contact properties like that. So it's basically a table, which consists of all the information of every type of contacts, and we can use it to apply or modify the contact property.
Excellent. That is correct. So every time a contact forms in PFC, it goes to this table to decide what contact model to put there, and also what properties to assign to that contact. And this is very powerful because it can have different, you can say if it's a ball contact, do this. If it's a ball wall contact, do something else. For example, let's try to do that. Let's go back to this one here. So the properties Kn, Ks are the same, 1e6, friction is 0.5. So let's run this. And what this is going to do is the friction coefficient will now be 0.5 everywhere. Let's see. How do we know that? How the heck do I know what the friction coefficient is right here, for example? So this is a contact. So let's go and turn off the force chains. Let's use a contact plot item. Whoa, it's drawing this big cylinder. So I say contact plot item, see right here on the right, and shape is cylinder. Let's make shape be sphere. There we go. So that's a contact. If I do this little guy with it's a pointer with a question mark. If I choose that and I click on this, it's going to tell me all information associated with this contact. So one of the bits of information is the ID number. It's an integer. Every single contact has a unique ID number. It tells me what we call the type of the contact. This is a contact between two balls. So it's called a ball-ball contact. If I go and look at this one, this is called a ball facet contact. Because this is between a ball, and it really is between a ball and a wall. The wall is made up of linear facets. And every contact in PFC is only between two things. So it's between a ball and a particular facet of a wall. And so we call this a ball facet contact. Okay. Now let's look some more. Click on this. Oh my God, it's everything. Position, unit normal direction. Let's look at the friction coefficient. Contact model. Where is that thing? Right there. I can't make this bigger, but right here, these are contact model properties. Friction, 0.5. Okay. If I go to this one, the ball wall contact, it should also be, it is 0.5. Now, let's run the model again and set it up so that all the walls are frictionless. How would we do that? We're going to use this magic CMAT. We're going to tell the CMAT that if it's a ball contact, give it a friction of 0.5, but if it's a ball facet contact, give it a value of 0. Make sense? So how we do that, I'm going to comment out the original command. So instead of saying default for every single thing be the same, I think I just say, Shihang, is this right? I'm going to put a return after this and run it and see if this is the right command.
We need a type.
Okay, instead of that, you got to say the type. So the type of contact, ball, and I don't know if I put quotes there or not. God, I think I do this. I'm going to have to look up the command. Both me and Shihong do not exactly have it right. I'm going to select it and hit F1, I think. F3? F5? Oh, come on. F5. Let's go. Well, let's just select that one.
Or maybe the method.
Hang on. Yeah, well, let's see. Okay, it's F1. And I couldn't get that to go to that, so now I'm going to have to find in the manual PFC, contacts and contact models, commands, CMAT. CMAT, what the heck? CMAT default. Oh, you still have to say the default. And then if you say the type, this is optional. These triangle brackets mean that this part of the command is optional. So, and what's a type? If the optional keyword type is issued, then it must be followed by a valid contact type name. Well, what are those? See this figure. Here's the figure. These are all the possible combinations of two things that can be at a contact. Here's what we're interested. You can have ball, because what do you have? You have balls, you have clumps, but clumps are made of pebbles. Walls, but walls are made of facets. And then you have rigid blocks. And so you have all the possible combinations of these. And this is symmetric, right? So if I have a ball, if I have a ball pebble, I also have a pebble ball, but it doesn't care. It's still going to be the same thing. So these are all the types, right? So we're going to do ball, ball, and ball facet in our model. That's all we have in our model. Notice facet is not applicable because the walls do not push against each other. The walls only push against balls. Okay, so the walls are just surfaces that you tell them to move. You give them velocities. So there's no, you don't get contacts between them. Okay, is everybody with me? Give me a yes or no. Yes, yes.
Yeah.
Yes.
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 Excellent. So contact, CMAT, default, type, ball, and I don't know if I give it quotes or not. Let's see.
No, you don't.
You don't. Well, it worked. Maybe
Interesting.
it'll work both. Hold on. Let's go to the command. Oh, what the heck happened to the command? Cut it down. Hang on. F1? For some reason it's, oh, there it goes. Okay. Contact, CMAT, default. S, it says
Type.
S type. It says a string. I click it, it says a string. So if it's a string, it's supposed to have, strings are always in quotes.
Okay.
So let's do that. Let's just see if it went through. It did.
Yes.
So now do the same thing, but change the friction and change the type. So what's the type now? Ball what?
Facet.
Cool. And we're going to put 0, right? So let's see if that runs. Does. Now let's run the whole model and then let's explore it. There, we're still zoomed in at that location where they packed in. Now they're going to pack differently. And it's solving here to an average ratio of 1e minus 5. Looks like this part is not moving around anymore. There's my system.
Oh, it's actually moved.
It did. I know. It's kind of cool. It was like these things are so sensitive, just like a sand pile on your desk. If you vibrate your desk, the thing wants to rearrange. It's very sensitive, and that's what these systems are the same thing. So let's zoom in here and see. This guy with the question mark. Click now. So what this friction be? What should the value be here?
0.5.
0.5.
0.5. So click friction 0.5. So far so good. This guy friction 0. Hey, I think we got it. Now let's make sure though. So I could go through here if I was really crazy and I could click every single one and see, or I could use the plotting logic. So here we go. Contact plot item has attributes. And what I want to look at is numeric values that are associated with contacts. So One of these is properties. There it is, fric. And I can, let's do named. Holy smokes, look at this. Let's change the colors, color option. I don't know, blue, there. So contact friction is 0 at the blue guys. We should see blue guys all around the wall. Look at that, that's so cool. And we should see red guys of 0.5 right there. Is everybody with me?
Yes.
Okay. Now let's keep exploring this plot item while we're at it here. We can also notice the color off says either named or scaled. Now, why would you do scale? Scale is going to give colors here. They're going to range from 0 to 0.5. In this case, there's only 2 values, so we don't really care. But let's go and get something that has differences. So let's look at the property of the radius. No, that's not going to be a property of a contact. That's different.
Force?
Sorry, go ahead.
I was saying maybe force. Can we?
Yeah, okay. I think we can get magnitude of the force.
It's in
Oh, we can-
vector. Okay.
Yeah, that's a different. Oh, yeah. Okay. Vector quantity. A force is a
Force.
vector quantity.
Okay.
And notice it's actually force magnitude because we're just drawing it as a sphere. We're drawing the shape of a sphere. So this is, let's see if this is making sense. It's kind of hard to do. So let's click. So this one is a lighter color. So this is bigger. This one should be bigger than the other one. What's the force here? Where's the force? Linear force, 246 minus 46. And this one is 2913, so it's smaller. And so here we go. Oh, we should see, what should we see in general if we look at this picture in terms of the difference from the top to the bottom?
The highest force at the bottom.
Exactly. And so red and green are high. And so you can see the higher ones are down here, lower ones are up there, right? So the plotting is like really powerful. Okay. I can also do things like let's just keep talking about this while we're at it here. So I could draw the shape as a sphere. I could draw the shape as a cylinder. And now I'm going to have each line there. And I can use, if I hit shape, I can control the size. So scale is 1. Let's make the scale be 0.3. And so now that's the length of it. And there's another thing, radius factor, which will control the radius of it, of the thickness, if you will. And all sorts of other things. Okay. We're just going to use sphere. Okay. Now there's another thing here. Shape says shape is arrow. So think of it as at every contact, there's 3 possible ways I'm going to draw it. I'm going to draw it as a cylinder, I'm going to draw it as a sphere, or I'm going to draw it as an arrow. Why would I want to draw it as an arrow? For example, and this is not a good example. Hold on, let me go back. Let me change this and let's look at the ball plot item. Hang on, go back to sphere. Okay, turn this off. If I click it, it's off. Let's go and create a ball plot item. Here we go. Turn off the one above. I just want this one. Refresh the thing. Oh yeah, the green is the color by default. There, make them red. Make them yellow so I don't get confused. Okay, ball. And the shape is a ball. But I can make the shape as an arrow. So what if I want to, for example, look at the current velocity vector associated with each one of these, because velocity is a vector, right? So we're going to draw it as an arrow. So we're going to say ball, at the center of every ball, I want to put an arrow, which is going to be the velocity vector. So I'm going to say shape, arrow, and then I have to choose what? So vector quantity, that was the default. There's all kinds of different vector. Here we go, velocity. and it's showing me the velocity vectors. And I'll turn on the ball up top, okay? And so it's drawing these with the back right at the center, and it's drawing them in the direction of the vector. And if I go to this, I can do things like scale by magnitude. And you can see what's happening. This guy is going still pretty fast because he's not actually doesn't even have any contacts. He just is sitting here. So he's rolling across. So that's dwarfing. It's much bigger value than everybody else because they're all really small. So instead of, I turn off scale by mag. Now they're all going to be the same length, but they're going to be colored over here based on their value. So this big value is that guy, and these are all much, much smaller relative to that. Is everybody with me here? Yes, yes, no, yes?
Yes, yes.
Yes.
Yes?
Yes.
Yes.
And so let's say I just want to look in here so I can control the contour interval here, right? So ball, arrow, I say color option. So it's scaled. That means I'm going to get this contour thing, and it's automatically choosing the max and min, right? But these guys, they're all smaller. So I don't know, let's go 1E 0 to 3E minus 4. So minimum 0 and then 3E minus 4. Well, I'm not quite getting this here. Oh, and then interval. Yeah, let's not worry about this. You get the idea, though, right? We can fine tune this stuff. Okay. There's 3 kinds of shapes, and so if you want to see a vector field, you need to draw the shape as an arrow. Okay. So let's go back just a ball. Let's get rid of this. Look at another thing about the contacts. So there we go, force magnitude. Let's look at the gap. The gap between every contact has a gap. For example, if I click this guy, in there is a gap. It's minus 1.6 millimeters. If the gap's positive, they're not touching. If the gap is negative, they're overlapping. And we remember in PFC, it's a soft contact model. The particles do not change shape, but they overlap, and there's a spring in there. And so we can color by the gap, right? And I'm going to hope that there's going to be more negative gap at the bottom and less at the top. So let's see. Here we go. Draw them as spheres. It's a numeric value gap. Here we go. Turn off the balls. And we're seeing red. Red is small, and this is bigger overlap. So blue. So there's bigger overlap at the bottom, right? Okay. So this is the way we can interrogate the model with this plotting. Okay. Another thing, if I just say text value attribute, then it just puts it back kind of like to a default. It just says over here, contact. It's also in the legend telling me how many contacts it's plotting. So it's plotting 394 different contacts here. Okay. Now, I'm going to do a little tricky thing. So it says contact, and there's this thing here called all contacts. And it's not checked. Now let's check it and see what the heck it does. Ooh, there's more. Do you see how when I click it, like right here, this guy suddenly is there, suddenly not there? Okay. What the heck is going? Color option, contact. Okay. So let's do in a second. What's this idea of all contacts? Does anyone know? You're probably any
I guess
normal person. Yeah, go ahead.
so. The active and inactive ones.
Correct. That's what this is about. So typically, and this is what any normal person would think if they didn't know what's going on in PFC, a contact means it's in contact, it's touching. However, we have a more generalized concept in PFC that a contact might exist, but it might not be active. Okay, so for example, two balls are touching, there's a linear contact model. Great, there's a contact there. There's a data structure called a contact that stores all this stuff that we looked at, like forces and things. If those balls now are pulled apart, that contact is no longer active. We define active as there's actually something going on there. There's a force there. And this doesn't necessarily correspond with overlap. Now, what if we take two particles and they're touching and so we have a contact, and now we put a bond in there, and now we move them apart, and the bond is really strong, so it doesn't break yet. So now there's actually a gap. They're not even touching, but they're still carrying a force because there's a bond. So that would still be an active contact. The other thing that goes on is that when two particles start to get close to each other, PFC will create contacts. And this is useful because in the overall logic, it's helpful to be able to know and start tracking these guys when they start getting close to each other, as opposed to just waiting until they're suddenly overlapping. And you cannot control that. But it's going to decide for itself. So let's look at this a little more clearly. We can still use all this other plotting stuff. So it says contact. Text value. That's not, yeah, contact type. So I want to show a contact type here. Whoa, there's a whole bunch of them. There is 4 possibilities. We have the types, ball, ball, but then we have some that are active and some that are inactive. And then we have ball facet. Let's close some of these down. If we look at color options, here's all the 4. Let's turn off the ball. Let's just do, these are just now the ball facet ones. And we got those 2 colors. So here's a good example. And let's make the active ones, I'm gonna click it, be red. And let's make the inactive ones be gray. So this guy's not active, this guy is. We'll see that guy's not touching. So that guy's inactive. Okay. And we're gonna see that there'll be a few places like here. Okay. This is like a very important part, PFC, when you start doing things like writing code that will like loop over all the contacts. Like you might want to write code that will loop over all the contacts on this wall and sum up forces or something like that. And so you need to know, so when you loop over things, sometimes you might just choose the active ones, sometimes you might choose all of them. Okay. All right. So that's an important thing. Usually when you're just looking at the physics of a model, you can just, you don't want to see all of them because they're not doing anything. So then you would not have all contacts checked. Okay. Hold on. Looks like she's having issues with her. Oh, she's back. Maybe she's back. I can see you. There you go. Are you back? Are you back? Okay, good. Okay. Contacts, all contacts. Oh, one last thing.
Yeah.
Good. Okay. So here's the thing we're looking at, contact type, right? And let's draw the shape as a cylinder. Okay. So there we go. It's not a sphere, it's a cylinder. By default, this cylinder is just going to go from the center to center. So for example, let's just look at the, what the heck? Contact type. What happened to my other ones? Why is it not showing me all of them? Hang on, let me choose it again. Shihang, help me. Why can't I see? I want to see. Oh, because I'm. Oh, yeah. Okay. It is showing. Wait, what? Oh. How come I'm not seeing the ball contacts? That's because I have the balls turned on. There we go. I just needed to redraw it. Okay. Hold on. So now I'm seeing ball, and ball facet. Let's change the color for the ball facet to be blue so that we can tell the difference, force it to redraw itself. Okay. Shape, cylinder. Now there's two other guys down here. It says directed and it says scale by force. Directed. I click directed. So if I hit directed, now it's actually going to be lined up in the direction of the force. And this we don't normally need to or want that, don't normally care about that if we just want to see these cylinder things. But if we're doing a force chain, how do we do a force chain plot? So contact, select it, shape cylinder, text value, force chain. But then we also need to say directed. So now it's in the direction of the force. And this thing about scale by force. Notice if I scale it by the force magnitude, the low forces are smaller. And so this is also going on here. And so now it's a contact force chain. I'm going to redraw it. I'm going to make compression be black, right? And this is what we've been seeing before. Okay. Let's delete that. Yeah, go ahead. Question? No? Okay. What else can we look at? We can look at the contact model, for example. So text value, model name, the name of the model. There it is, linear active. And if I click all contacts, it's also the linear, whoops. All contacts, make it refresh. It's not working. Come on, it got itself confused. Let's go back to model name. Doesn't want to do it. Let's just delete this. Come on. Contact. What were we doing here? Model name. I want to show linear active and linear inactive. So now if I click all contacts, there we go. There's the inactive ones and the active ones, right? So you can get the information with the plotting. You're usually going to get the information about the model. Question? You guys good?
Yeah, we're
Okay.
good.
Okay. You can get it with the plotting. You can get the information individually by clicking on the thing. So this applies to balls. This applies to walls. Any of the objects in there, I click on the facet. There's facet 2 of wall 2. Da, 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 da. There's all this information associated with it. Okay. I can also do a list command. So I can say contact list. And if I just say contact list, it gives me this crazy list of all the information. This is by default information. There's the ID, there's the type, contacts between two things, N1, N2. Has a position, right? Gives me all kinds of stuff. Let's look at, so I can say contact list property. There's a contact ID 4, ball, linear contact model, and here's all the properties, right? There's something called range logic. I can say contact list property, but I want to kind of filter it. I only want to see some of them. So I can say contact list property. What does that mean? Range, type, ball facet. And it's supposed to say range contact type. And so now it's only going to list the ones that are ball facets. Okay. And what if I only want to list the one with ID 6? I can, this range logic is very powerful. F3 there. Contact type, ball facet, ID 6. Union, no, just, yeah, I want to, which guy? I'm going to show, I want to say all the ball facet contacts and the ones that have ID 6. So we're only going to get that guy. Okay. So that's the range logic, and we'll talk about that a little bit more later. That's a very thing we use all the time to delimit the commands so they only apply to some guys. Okay. Okay. So now we have that frictionless. Oh, and let's look. How do we know that it's frictionless? If we look at this picture, let's look at the force chains. Now I've lost the stuff over here, and I think I hit this guy. There's a little arrow going to the left that gives me this guy back here. And I want to look at, and let's zoom in here. Now, what is a characteristic of the force chains against the wall that they should have if the friction coefficient is 0?
They are perpendicular.
Correct. This is the orientation of the force. And if there's no friction, there's no component this way. So the final direction is always perpendicular to the two bodies. Notice here, there's not 0 friction. They're not. So watch, let's run it with 0 friction everywhere. They should all be perpendicular now. PFC got a little confused. It's not updating itself. Let's just run it again. Easier. Here we go. Now they should line up. And so notice all the contacts now are straight. They're going to be, for discs, they're going to be center to center. Right? Okay. And while we're talking about it, let's illustrate one other point. So let's now give these real friction, like a real granular material. So let's say 0.5. They're both going to be 0.5. Let's run this. Let's look at the system. Now I'm going to ask a question, and Ayat can't answer it because she's going to know the answer. Let's see if you guys get this now. So here now, okay, it's trying to come. It's still slightly rearranging. You can see the force chains changing here. Here's your ratio. We're trying to get to 1e minus 5. Still rearranging. These guys are still changing a little here. They're still slightly moving. And good enough. Here we go. Static equilibrium. This is what the pile looks like. Now, what's going to happen if at this point I set the friction coefficient of all contacts to 0 and continue to cycle? Is anything going to change? Young King, what do you think? Are you there? No, she's not there. Bowen, what do you think?
If we don't have friction, maybe the distribute of both will be more uniform.
More uniform, probably. Yep. What else will happen here? What if, think of let's just do it. So I'm going to give a command, contact property command. Contact property, which property? Fric, 0, boom. So the property fric has been set to 0 for all contacts here, 472. Think about this, for example. This guy here. Trying to get a good example here. Like right here, there's a shear force here because this is not center to center. Suddenly that shear component is not going to be able to be there. Okay. Up here is a better example. Here, there's actually this particle. There's a shear force pushing this way, and there's a shear force pushing this way. That's kind of helping to hold them. If there's no shear forces, the system, so I'm just going to say cycle, some giant number, million. It's rearranging again. And what's the difference? Is there a way to measure something about this macroscopic system that would indicate a change? What happened to the packing in terms of its structure, in terms of how much space it filled? Let's do it again here for a second. We can just go to that save state. I'm double clicking on the save state because at the end of that last one, we did a save gravity pack. So here we go. This is, and there's friction, non-zero friction. Cycle a million, nothing happens. I'm cycling. See, I'm cycling, nothing's changing, right? So look kind of like look at where like the top surface is right now. And now let's say give zero friction. Contact property fric 0. Here we go. Watch the top surface. What's the top surface doing? You can answer, Ayat.
I think it's rearranging to the densest state. So when we were looking to the curve of the shear, there is no limit. So it's continuous shearing and the shear force is building up with nonstop, basically.
Well, locally, there's no shear force anymore because there's zero friction. And the system is getting more dense. You can think of it like if I had very, very friction, high roughness, and I put them in a box, they would reach some state. But then if I remove the roughness, there's less ability to hold that shape. And so they're going to get closer together.
Yes.
Like if you want to get the most dense packing, you would want to have a zero friction coefficient. It turns out that it's the friction coefficient that's providing the strength of a granular material. And so that's like a key element here in terms of if you think of one of the things people want to measure for a granular material is the porosity. What's the porosity going to be? And you may know if you've done like tests on sands in a laboratory, you put them into a cylinder and you do it very carefully and you slowly pour it in and you get a certain porosity. And depending upon the size distribution and other aspects of the material, it'll be different for different materials. And so one of the things that controls that is the friction, the roughness. Okay. And then other thing is that this thing is controlled also. You could, if you took a specimen of sand, here's the question. You took a specimen of dry sand, you slowly poured it into a cylinder and it's sitting there. And what if you took that thing now, like it was a coffee cup on your desk filled with sand, and now you like hit it up and down a few times? What would happen to that system?
It's going to settle more.
Going to settle more. Exactly. So this is actually done by people who are often trying to make it. Turns out that the initial porosity of a granular material is fundamentally controlling how it behaves. The lower the porosity, the kind of stronger the material is, the stiffer the material is. And so this is quite a key thing.
I just have one question here. So for example, I know the material that I am packing have a rough surface. So when I pack it, I shouldn't use friction coefficient of 0, or if I want to reach the densest state, I still have to use friction coefficient of 0.
Well, if you want it to be like your real material, you should use the real friction coefficient always. And then you should try to build the specimen in the same way you do in the laboratory. So if that means you were pouring it in from 500 millimeters on above, you should do the same thing with the model. And then the model will achieve whatever the state it wants to achieve. Does that make sense?
Yeah. Yeah.
Okay. And you could play games with things if you know, let's not even worry about that. Yeah, that's what you should do. Okay. So are we good? This making sense?
Yeah.
Okay, good. Oh, last thing. We can also look at this porosity. No, where is this? Here we go. So this sucker here. Let's go back to the gravity packed state. I'm going to double click on this. This is the one where we had friction of 0.5 everywhere, and this equilibrium. And one way to measure the porosity, a crude way, but this is what you would do in a laboratory, is you would look at the height. And if you know the height of the pile, you know the volume, and you can, if you know the amount of stuff you put in, you can back calculate the porosity. And so if the height gets lower, that means it gets less porous, right? So that could be a crude way to do this. But in PFC, we can actually create a region. And in that region, we can actually measure directly the porosity, because the porosity is, you know, the volume of voids over the volume of the region. And so in PFC, we can define these regions. The regions are going to be disc-shaped, circle-shaped in 2D, and they're called measurement regions. Okay, and so you can compute different quantities, different average quantities over those regions. So to do that, I have to create a measurement circle, and I think I say measure, create, let's call it measurement region ID5, and I have to give it a position. And I think in this model, this is 0, 0, and I think this is 2. So the position is going to, and I don't know how high this is. We'll just have to do trial and error. Position X coordinate 1, Y coordinate 0.3, and radius 0.3. Now I'm going to use a measurement plot item. So I go to my list of plot items, and somewhere in here it says measure. Here we go. And I kind of missed my position there. So let's go and actually do it in the data file. Measure. What was it again? Create ID5 position. Put it right in the middle, 1, 0, and radius 0.3. Let's just run that. Let's look at it. Okay, I don't want it there. I want it way down here. Oh, okay. Why is 0? Where's my 0 coordinate here? I'm confused. Oh, okay. This is, yeah, just a second. This is 2 meters. Help me. So if this is 2 meters, I want this thing at, I don't know, like 0.4. See if that's better. How come it didn't change? 0.1. Boom. Well, this is exciting. Why is it not changing? Help me. Delete that. Make another measurement region. Why is my measurement region sitting at up
Can we
there?
see the wall coordinates, please?
Yeah. There's my X. Oh, they're up here. This is 0, 0. Okay. Thank you.
I think it was minus.
So we want to go like, I don't know, minus 1.5. Let's just see where that puts it. There,
Yes.
better. And let's make some more particles if we can succeed. Do 500. We probably got to make them smaller. Let's just see if we can get that many from those sizes. It gave me 359 out of 500. Let's make them a little bit smaller. 0.4, 0.3 to 0.4. Got to be 480. Close enough. Let's run this thing. So we got the measurement circle in there. We got the ball. We got 0.5 friction. So that's just the place that's it's going to make, we're going to ask it, it's going to measure different things. So it's not actually doing anything. So here we go. We're trying to get our pack. PFC quit updating the plot. We're going to say we're close enough. Well, let's get it there to equilibrium. That's probably a good place to measure. Okay, there we go. There we go. Now, there's a bug in PFC. You're supposed to be able to type measure list, and it's going to dump out all this information about every measurement circle. There's a bug right now. So I'm just going to do this. I'm going to do a fish call, measure porosity. I think this is the command of measurement circle 5. Sorry about this.
Do you need to do measure find first?
Yeah, I think you're actually right. There. So let's not worry about this detail. This is the porosity that measurement circle 5 has just computed. It's 0.228. Okay. 0.228. Let's change the friction to 0. Cycle a bunch. And now you can see it's settling. So we would expect it to be less porous. Here's the region we're going to measure in. So there's less gaps in there now in that region. Let's stop the cycling and let's ask for again measure porous. So now it's 0.15. Okay. Question. The porosity that I'm measuring in this 2D model. Now this is the porosity of these discs. Remember, these are unit thickness discs. So it's in that region, it's the ratio of the voids. There you go, voids over whatever that size region is of discs. Now, is that going to be the same if I look at like a packing of spheres in 3 dimensions? Would I have the same? Like if I do a packing of spheres of this size into a big box, would you expect the porosity to also be 0.15?
No.
Why not?
Because it's 3D, and we got like for uniform sphere, we have the minimum porosity like nearly 0.6 or 0.36 or so, and in 2D is about 0.15. Yeah, it's nearly the minimum porosity. It's about
Correct.
a dimension. Yeah.
So what Shihang is pointing out is that the 3D measurement is very different because it's a 3-dimensional system of particles and it's not unit thickness disks. And then he was illustrating that with the fact that if you take disks that are the same size and you pack them as close as you can, which is what we saw before, that crystalline arrangement, you're going to get, what did you say, 0.15 or 0.08 or something? And if you do the same thing with spheres, they'll pack to like 0.336, 0.32, something like that. It's a physical thing, right? So this two-dimensional porosity in PFC2D is kind of a relative, well, it's a measure of the disks, but it cannot be compared directly to a 3D thing because it's a whole different system. Okay. Let's look at one more thing here since we're doing this. Let's use the history logic and let's monitor the porosity in that measurement location. So how are we going to do that? So here, we already had created a history, which was the total force in the y direction on the bottom facet, which was the wall, which was named MV bottom. Let's recall that. We were able to use the history plot item and this was the force on the bottom wall that we were monitoring, right? They bounced, the force got really big, very big negative, boom. Then they bounced up again. Now it's settling. Now it's at equilibrium. Then we suddenly changed the friction to 0. So suddenly the force dropped and now it's resettling itself and it's almost at a new equilibrium, right? This is the history mechanism. So let's make another history, which is going to be the porosity in there. So what am I going to do? I'm going to say, I think I'm going to say measure. It's a history about the measurement logic. It's not a history about the walls. All the commands in PFC, the first word is typically going to be the thing that you're doing, right? You're doing things to balls. So you've got a ball something command. You're doing things to walls, wall something, right? So measure history, let's give it a name. Poros in, let's just call it Poros 5. And now, in fact, this is not going to work. I'm going to have to create, help me here, fish. Okay. I have to make a fish function. Fish define, is it define fish? Define fish. I think it's, help me, Shihang. Is it fish define? I'm losing my
Fish
mind here.
define or just, yeah, fish define.
Gonna
Or,
make
or
a fish
just
function.
define.
Here we go. We're
Yeah.
gonna learn about fish. Fish define Poros 5. And this is the fish function. And inside of there, it's going to return something. And what it's going to return is the porosity of measurement circle 5. This is finding the pointer to measurement circle 5, and this is returning the porosity of whatever that thing is. Let's just do return, make sure that goes through. Looks good. So now it's actually, it's not a measure history, it's a fish. We can take a history of a fish variable. So fish history, call it Poros 5. And then I think I give the name of the fish variable. Let's see. Created history called Poros 5, and it's a fish thing. What histories do I have in the model? History list. Have this force on bottom wall, Poros 5, right? So, yeah, it's a fish function. Okay. So now there, let's run this. That's the force on the bottom wall. Let's look at the balls here. They're settling. There's the forces. Let's add over here another history chart plus, and I can do this while it's running. History chart. Turn off that history. Let's turn off all this other stuff for the moment. History. Notice it says, here's the two possibilities. So click Poros 5. Oh, and it's probably not going to be able, I really can't do things with it while it's running. So let's stop it from running. I hit escape, shift escape. History, Poros 5, boom. Here we go. Poros 5 versus step number. There was some, it was just one because it wasn't doing anything. And here we go. And it looks like it's getting to series, make it a color red so I can see it better. Turn off this. Let's run it again. Let's just look at that porosity. It's cycling. There we go. Right, it's packing in that region, right? Porosity is getting smaller, smaller, really not changing much anymore. Okay. All right. Make sense? You guys all with me?
Yes.
Yeah.
We've kind of covered here everything about PFC at this point. And you can see how general it is, right? Because I can make a function and the function can do anything I want and I can hook it into the history. So now I can make plots as things are happening of all sorts of different stuff, right? So good enough. I want to show one more thing and then we'll take the break. Okay. So we've got our simple system here where we can build these packs of particles. Let's just go back to this. And these are disks, right? And let's turn those off. Okay. And this guy has 480 of them because we use this command called generate. Okay. And it's just going to give us an arbitrary collection of particles that are disks, that are balls, that have radiuses with uniform distribution of sizes from 0.03 to 0.04. It's going to try to make 500. Okay. Boom. Boom. Show the balls. Come on. Oh, they're up. Where are they? Come on. Why is it not showing me the balls? Because I didn't turn them on. There they are, right? 480 of them. But what we typically want to do is we want to generate a given size distribution of particles. Okay. And does everybody know what a size distribution is? Somebody tell me. Size distribution. What's a particle granular material size distribution? Come on, somebody knows this.
Well, is that something like we have a different percent number of the balls with different radius?
Yes, exactly. So here I'm going to actually go to the PFC manual. And in the world of PFC, there's a whole section here called bonded particle modeling. And in there, I talk about PFC model essentials. These are things that fundamental you should know about. And one of them is a whole little description right here about what is a particle size distribution. And this is what you were talking about. This is how it's usually expressed. So this is particle size, diameter in this case, and this is, they talk about percent passing. So this would mean if you had a sieve, that's what you have. If you had a sieve and you put sand and you shake it, there's going to be some that are left on that sieve. And so this would say if the particles are bigger than this size, 100% are left on that sieve, which means they're all bigger than that. And then what you have is a pile of sieves. Then as you go down, they're smaller. And so then you say these are smaller. And so now at this point, so from here to here, that's going to be 10% of all the mass. And from here to here, they're smaller and they're smaller. And so this is going to be your minimum particle size, and this is going to be your maximum. And this is what people use as a very fundamental thing to talk about granular materials, to characterize the first pass to characterize them as size distribution. And this has a big impact on behavior. Like, for example, if you have a lot of little tiny particles in between all the gaps of the big particles, that's going to make the system more dense and stronger. And all of that is reflected in this size distribution thing. Okay, so how do we do that in PFC? right? We're going to actually use, so how do we generate that first? So we want to be able to create, we want to say, I know the size distribution, and I want to generate a collection of disks that satisfy that. That's what we want to do. So we can't use this ball generate command. So there's going to be a different one called ball distribute. And this is going to create a distribution, a size distribution of balls. Okay. And so let's just see if we can figure this out, and then we'll go look at the command as needed. So it's for sure going to have to know where to make these balls. So it's going to have the same concept of what's the region. So here it'll be this box thing. So in that region, I want to create a size distribution of particles. Now, what's the next thing that I have to do? I'm going to have to tell it, I have to break this up into, I'm going to think of like volume fractions. So this thing, let's say this is the curve that we want to generate, particles from this size distribution. So for this curve, I could say, oh, well, 10% by volume, actually by mass, if the density is the same, it's by volume. 10% of the volume has diameters from here to here. And I would tell it that. And then I could say diameters from here to here, to here, that's going to be 80% of the volume. And then diameters from here to here is going to be the remaining 20%. I'm going to carve this up, and I'm going to say over this size range, make a uniform distribution from D1 to D2, and 20% by volume will be that. And then make another one, okay? Get the idea? Yes? No?
Yes.
Yes?
Yeah. Yes.
Okay.
Yes.
So somehow, I'm just guessing here, I'm trying to remember. I'm going to put 3 dots because that means I can now, the command, it's a line continuation. So instead of putting all this in one giant line, I can now go to the next line. Okay, so I need to give the box. I'm going to say bins 2. I'm going to somehow have to tell it how many chunks. So let's just do 2 chunks as a simple example to begin with. And now I'm going to have to give the sizes and the volume fraction. So let's actually look up the command. I'm going to hit F1, and if we're lucky, it's going to say ball distribute. There it is, ball distribute. Bin. So specify the properties in that bin. So yes, low and high. So bins 2. And then I think I say number. Okay, first I say number bins. See if we get this right. Number bins. Bin 1. Sorry. I think I do. Bin number, bin 1. And I radius, low, high. Radius, low, high. 0.03. 0.04. And then I also have to say volume fraction. Volume fraction 0.5, half of the volume. And then for the other bin, let's just screw around with this. Let's make this the same size, but then let's make the other ones bigger. There. This is saying half by volume are all 0.03 and half by volume are 0.04. And let's see if that's the right syntax for the command, ... Let's run it. It's probably not. Oh, I guess I got it. Let's look. 928 balls were generated. Something right away that I noticed balls. Let me run the other command and tell me what you see about the balls. The generate. What's the difference between this and the previous one? These guys are not overlapping. These guys, when I use the ball distribute command, are overlapping. Okay. And this is because there's one other thing here we need to talk about. And this is the thing I didn't give. Think of it this way. I'm telling it to use particles. Half of the volume has this size and the other half has that size. That's fine. But I didn't really tell it how many particles, right? I mean, this is a size distribution, but I could make 10 trillion of them that satisfy that, or I could make 17, right? And we don't really want to say a number because that's really weird and complicated, right? Because if I change the size distribution and I want to fill a certain space, I don't want to have to always keep guessing what the number should be, okay? So we're going to create this, we're going to have this idea of I'll call it a cloud porosity. And we're going to say porosity, and let's do 0.8, some really 0.9, really highly porous. It's going to take particles from this size distribution and randomly insert them until the porosity of how many it's got in that region is 0.9. And it doesn't care if they overlap. So let's do 0.9. And this is porosity of 0.9. That's how many balls I got, 109. If I say, no, I want that, I want to make a lot more of them. So now porosity of 0.4, I run it again. Now I got 652. Okay. Now let's look at the size distribution before we do anything else. Okay. So in PFC, you can use that measure logic, and there's a way to get out size distribution. Instead, and partly as an example of doing of something else here, is we're going to use a fish function that I have created that one can use that I think is actually a little more powerful in general than what's in the measurement logic. And we're going to use that to tell us the porosity. Okay. So first of all, where is that? There's a little, it's sitting here. It's a file, psd.fish, psd, particle size distribution. And we don't need to care about the details of it, but this is what it looks like. These are fish functions, fish define, okay? So we're gonna stuck in this. It's just like think of it as like a Python package. You're just like calling in a certain package and it's gonna provide you the ability to do something, okay? So we're gonna suck this in. So I'm gonna at the top, somewhere after the model new, I'm gonna say program call, and it's gonna look at, this is gonna suck in this fish file. It's gonna process it line by line. And it just did here. You can see it said fish and it's going line by line. And at this point now, I can call those functions. They're loaded, if you want to think of it that way. Is everybody with me? Okay.
Yes.
Yes?
Okay.
No? Okay.
Yeah, okay.
And this is all documented here in this in this bonded particle modeling where it talks about size distribution. I know it's not actually in here. It's actually in something else. It's in the material modeling support package, which is what we use to create bonded assemblies. There's a function we're going to call, just one, that's going to actually now compute the size distribution. And that function, I'm going to have to try to find it. It should be this. Just a second. Right here. PSD mass measure. Measure the particle size distribution of the sample. So here we go. So after the command, I'm going to call a fish. I want to call a fish function. So I have to put it in square brackets. And this fish function when you measure the size distribution, you need to tell it this is going to make that size distribution is really a histogram. And it's going to basically look at, in this range, what's the size distribution? In that range, how many are in each of those things? So we need to tell it the bins. Let's just run this, see what happens. Sum of the mass is 0. Okay, because it's trying to do a size distribution, so it needs to know the mass, because it's mass passing, right? So I can't call this here yet because I haven't given a density, right? Down here. So after I give the density, I'm going to try to call it. With me?
Yes.
Okay,
Yes.
here we go. Measure. Okay, looks like it may have worked. Now, I can now make a plot item to take out that size distribution. So, just here going on the fly, just a second. I need to find. We'll talk about this material modeling support package later. It is, and in here talks about using this. And it talks about it in where is this thing? Help me. IAT. I can't remember where this thing is.
I'm not sure
Microstructural
here.
properties. I think that's where it is. Here it is. Remember this plot? Here we go. The grain size distribution is computed. Okay, hang on. We're supposed to call GSD measure. No, yeah, this is old. PSD sorry. Yeah, it's PSD mash measure. This is out of date. Just a second. Sorry about this. There should be 2 tables existing here. Hang on, let's run this thing again. I'll show you what this is. Table list, here we go. We can create these things called tables, which are XY data points, and we can also plot them in PFC. So we want to plot mass passing versus what? Versus grain size. And yeah, that's what should be in there. Okay, let's see what happens here. My view, I'm going to make a table plot item because that table should now have been created. Hang on, table chart. Turn off everything else. Here we go. There's two tables. I want the one called mass passing. Boom. Here we go. This y-axis now should be going from 0 to 100, which is the percent mass passing, and this should be the grain size. So just to make this better here, let's label these things. So I say mass passing percent. So the y-axis, mass passing as a percentage. And the x-axis is grain size. So let's make the x-axis say grain size in meters. So let's see if this actually worked. This says that all the particles have grain sizes between 0.06, 60 millimeters, and 80 millimeters. And grain size is defined as diameter here. So we should have half of the volume, half of the mass should be 0.06, and half of it should be 0.08. And I think that's what we have.
Yes.
Yes. Okay. So let's now, and so yeah, let's just test this again a little bit here. Let's make these even smaller. Let's do a more 0.02. There we go. Oh, let's just do it. Yeah. 0.2, 0.8. Now it'll be more noticeable. There we go. We got some bigger ones. We got a whole bunch of them. 20% of them are these smaller ones and 80% are these bigger ones. And we should be able to see that. Now there's one other thing here. There's all this because there's this crazy overlap. It even says there may be huge overlaps. There's going to be really big forces initially because the force is stiffness times overlap. And so there's going to be this massive force that's going to push these and accelerate these apart. And if we don't do something about that, these guys are going to fly apart at really high velocities. Okay. And so what we're going to do is when we cycle this, the beginning, so this is all still the same, but before we do the solve, we're going to say model cycle. We're going to say, let's go 2000. We're going to say this thing calm. What does that mean? This means it's going to take 2000 steps, but after each step, it's going to reset the velocities to 0. So if we watch this thing, look at the force chains, it just like pushed apart. Let's look closer. Let's put a pause here. Here's the overlaps. Let's just do cycle 1. Big giant forces in between those suckers here. Cycle 1, let's do cycle 10. Cycle 50, you can see they're pushing apart. And they're rearranging. They're actually pushing apart at very high velocities here. So we want them not to have such high velocities. So we're just going to do this. And now we do just what we did before. So let's look at this thing, see if we got this here. Oh, come on. It's the here we go. Turn on the walls. And that is annoying. It's plotting. Oh. So we're cycling 2000. That's what's taking so long. And now it's going to fall in there. Because they pushed apart, some of them are actually going to fall out here. We're not going to worry about that. And now here, this is just the normal thing. This is what we did before. Now it's just building up this pile. Okay. So it's the same thing as before, except now we have the ability to specify the size distribution by using the distribute command. Okay. And a key element, again, is this porosity. It's going to determine how many particles we get. So if I do 0.4 and I look at the view, it made 550 particles. If I make it even lower, instead of 550, now it had to put 735. But the lower I make, now it's going to be like massively packed and stuff. So you're going to end up wanting to use a number that's kind of a reasonable, maybe 0.4 or something like that. Okay. So that's what I wanted to show. And let's take a break here. Let's just let this run and get itself packed. And let's take, so first of all, does this make sense? Do you get the idea?
Yeah, we got the idea.
Okay. Okay. And I'll just say before we do the break here, there's this, everything we're doing is for balls, a ball distribute, but there's an exact same command for rigid block distribute. And so then I could also make a size distribution of rigid blocks. And we would then have to give the shapes of the rigid blocks and say how many of them, what's the volume fraction of a certain shape and what's the volume fraction of a different shape. But the commands are all the same, okay? Everything we're doing here with this simple model is all just being done with PFC2D with balls, but all the same concepts apply to clumps or rigid blocks, and all the same things apply to the PFC3D. Okay, so this thing that we're going through is like covering all of the basic aspects of working with PFC. Okay, so here's what we're going to do. We're going to take a 15-minute break. When we come back, we're going to look at these slides and we're going to sort of formally talk about the user interface and the history and the logic and stuff. And at this point, that should sort of all make sense to you because we've already talked indirectly about histories and a little bit about, you know, these different things. Okay, so let's take a 15-minute break. I will put this up. All right. So graphical user interface. What do you need to know to work with PFC? This is, oh geez, yeah, we got to have some quotes here. Talking about well-designed things. This is going to date me because you don't know what this brand new digital watch, right? Do you guys know what a digital watch is? Probably not. Well, you know, people used to wear watches. This is a question. Do any of you wear watches? Yes, no, everybody. Sorry?
Yeah, of
We
course,
have
we're
watched.
the new generation.
You guys, you do wear watches?
Yeah.
Well, digital, like smartwatches.
But you have your cell phone. Oh, they're
Well,
smartwatches. Okay, wait. So everyone who does have a watch has a smartwatch. Is that correct? Of the people here?
I have one.
Yes?
Yeah.
You have one. Okay. Oh man. Okay, that's right. Well, think of a really, really dumb smartwatch. That was a digital watch. And this is from 1988. And this was like a big deal. And only really, really engineering geeky people had them. And they were freakishly hard to use because they only had like 2 buttons on them. And you had to like have this giant manual to even just change the time would probably, you know, it would be super hard because the graphical user interface was not well designed. Okay, and that's what this is talking about. You would need an engineering degree from MIT just to work this thing, right? And so the question, of course, is this is a book about design. This is a very nice book, the design issues of design. So why should it take hours? Why is it not possible to make a good digital watch? This is 1988, by the way, and graphical user interfaces, there really wasn't any kind of concept of that. And so the technological things that were out there were just brutal. They were horrible to work with. And so here's an example of design, right? A well-designed object, you don't even have to think about what you're doing here, right? This is clearly a poorly designed object. So here you go. It's well-designed. It's easy. There are cues if it's well-designed. You don't have to read a manual, right? So here's a bench I made, and here's my son. I never even taught him anything. He couldn't even read the manual yet, and even I didn't write a manual for it, right? He just was able to figure out how to use it, right? And lo and behold, he's still able to figure out how to use it. Isn't this a fun picture? It's the same kid. It's not the same egg beater, though, I don't think. But and he wouldn't put it in his mouth. I tried to get him to do that, but he wouldn't do that. But he did sit down here. So I'm going to argue that the PFC user interface is a well-designed object. Okay. And so then this is essentially what we've been working with, right? Which we've gone through. That's all we need to do to make a packing of particles. And so I like to say this can be very intimidating at first, right? It's kind of like when you first see this, there's like all this stuff. It's like the cockpit of a 737. And there you go. This is actually my friend. That really is a 737. and it looks intimidating, but he will assure you once you've had a tiny bit of training, it's actually it's really not that hard. So PFC, I would argue, is the same thing. This whole idea, right, that we have a project, it lives in a directory, everything related to the model should be in that project, in that directory. When we open PFC, it allows us to either start a new project or to go and open an existing one, right? The name of the project, there it is. That's the file name. So that's going to be at the top, and it's going to tell you the code, and it's going to tell you the version number of the code. This is version 9, and then there's this other number after here, which is the subversion number. And every time that a small new feature or a bug gets fixed, this number gets incremented by 1. And all of this information is on our website, and it can be gotten from the code, and it will tell you what is the latest one that you have. So this is the latest current version. And if you're not running that, you should occasionally look at this and figure this and see if you're up to date. Okay. And so this has gotten here. Help. No, where is it? Just a second. Someone help me. Is it tools? Here we go. So tools, check modifications. And this goes off to the internet, puts you on that website. And here it tells me the latest one is 181. And that's the one, I believe, if you look at the top here, is what we're running. Okay. So that's the idea of this. There's built-in documentation. Something that I find helpful is if you click this box in the options, when you open the documentation, it comes up in its own web browser. If you don't do that, this pane over here on the right has the documentation. Some people like to use it that way. I think it takes up too much important real estate, and so I like to have a completely separate. So here's my browser, and this is a separate browser, right? This is just running. Sorry, this is just running in its own browser window, but that's not the default. So if you want that, you got to say tools options do this, and if you change anything like this, it's changing it in what's called the registry. So it's changing it on your machine, so it'll remember this in the future. Okay. The main thing we work with in PFC on the left here, you can see them all. You have data files, which are scripts that the code will execute line by line. There's something called plots, which are letting you visualize the model, and then at different times you can save data of the model so you can go back. And then you've got this console, which is showing you, it's echoing every command that it processes. And I like to call this guy here, the flashing little guy, that's the genie. Now, the Chinese people may not know what that is. Do you know what a genie is? Somebody. Ayat, I think this is a Middle Eastern thing, actually. Genie. Do you know what a genie is?
I don't think it's a Middle Eastern, but there is a song
It's
called
not.
Genie.
No, that's not what I'm talking about. Oh gosh, okay. I don't know what that is. Here's what it is. Have you heard of, there's a story about like someone finds a bottle, they open the bottle and cloud comes up and it looks like a person, it's a genie, and the genie says, I will grant you 3 wishes.
Yeah, it is actually in Arabic, Jinni.
Okay.
Yeah.
And so that's what I mean. The genie will grant you wishes. You can ask the genie to do something for you. And so that's what PFC does. See, it makes you happy. Every time you give a command, it's obeying your command, right? So I like to say that this console window is the command genie. It's just waiting for you. It's flashing, waiting for you to tell it what to do, okay? Here we have the editor window where you can look at your scripts. And there's a button here, and if you click it, it will execute starting at the top line by line. So every line, it'll get echoed here, and PFC will do that. And it will keep doing that until either it hits a pause, in which case it says you need to type continue. And if you type continue, it goes after those. It executes the lines after. And when it hits the word program return, it's done with this data file, and it comes back out to this level. But of course, there can be multiple levels. So inside a data file, halfway down, you can say program call a different data file, which means then the command genie goes to that file and starts executing it line by line. When it's done with that, comes back and continues where it used to be. Okay. So you control all this in the editor. The editor has nice, smart things. It'll have things. This is in green because it's a string. This knows that this command needs a command word called true, things like this. Okay. This is just I find to be a helpful thing. This cut or copy line at cursor is helpful because for me, like if I just want to take this line and just copy it and paste it, since I have that, whoops, that didn't work because I didn't hit it, Alt Edit Cut. I can say Alt Edit C and then Alt Edit P, copy paste. And so I find that to be a useful feature of the editor. Plotting. Who the heck knows what this thing is? What is that thing? What is it doing? What is it for? You think it is? What does it look like it's doing? They call it a plotter. This is an ink pen. And there's a system here of different colors. And this was a means by which you could do a very sophisticated thing in 1984, which was computer graphics. And you could do your graphics on a piece of paper. And they call this a plotter. Has any of you even heard of such a thing?
No?
No.
This is so amazing. So this
Yeah,
was, go ahead. Yeah. Have you heard of it? Is that Yun King? So this was like an architecture firm.
I never heard of it.
You've never heard it. Okay. So like architecture firms would have these to make their blueprints. If they were very sophisticated, this was a very fancy thing, very expensive thing. But you can see it can create color plots, right? There obviously were no laser printers around. Printers were just printing characters, letters, and then you could now do this cool thing called a plotter. And so this is actually the plotter. When I was an undergraduate, I was an intern at Itasca, and we had one of these. And it was like super cool. And it's super fun to watch because, you know, it goes really fast. So it looks like somebody, you know, it picks up a pen and it goes da 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 da, that lifts it up, moves it. You know, you get the idea. It's a pretty simple mechanical device, right? So these things used to exist. They were called plotters, and that's why we use the term plotting in PFC. Our codes are so old. They were all originally created in the world of Peter Kundal in the early 1980s. And they were pretty sophisticated because they had graphics. And so to make the graphic images, well, everybody at the time would say, are you making a plot? That's a plot. So that's the reason that we call it plot. Okay. So there it is. Now the plot is a synthetic thing on the screen, and it lives in its own window. So here you go. Here's the plot window. The plot window has a legend because the plot contains different items. So this plot, it's showing walls and it's showing balls. And how do you control that? That's over here. This is listing the plot items. that are going to be in the plot, and you can click them on or off, right? Each plot item has its own set of attributes, and we've been using this, right? Here's the ball plot item, and you can color things and all that stuff, okay? And the plots live over here. And what you will do is you make multiple plots. You make one that's zoomed in close, and then you might make one that's zoomed out far, and then you might make one that just is showing force chains or whatever. And by clicking on this, you can go between the different plots, okay? And there's nice little things, right? You might make a complicated plot, and then this button here will duplicate it. So it'll make a copy, and now it'll say system view copy. And then you can give it the right finger and you can rename it. And then you just maybe change a few things, right? This is that one. If I want to make a bitmap to suck into my PowerPoint, I can click this, and this entire plot window will be turned into a bitmap, which then lives on your disk and you can use it for things. There are settings related to the plotting, right? One of the most important is how often should the plot be refreshed during cycling. So while you're cycling, right, we've been watching these things rearrange, right? And so you need to tell PFC how often should it redraw the plot. Typically, you do not draw it every single time step because usually things are not changing much in a single time step. Also, the plotting is slow compared to the cycling logic, especially for large models. So this is an important thing. This is in options plots, right? Where's options? Here's PFC, tools, options, boom. And one of the things here is plots, and that's what I was showing, right? It also has things like the like picking. That's what we've been doing where we grab this guy and click on something, right? Okay. Okay. So there's plot settings. Speaking of picking, here we go. Remember using the pick tool. It's the pointer with a question mark. Click on something, boom, there you go, ball 29. Here's all the information. And then also, as you're doing this, as you're moving over this, it's constantly telling you in this information box what you're currently over. So if I look at this and I zoom in and I turn off my force chains and I hit that, look here. As I move, it's, oh, that's ball 638, that's ball 671, that's ball, etc. So that's this picking logic, if you will. Okay. Now let's talk about the kind of most important plot items. There's this ball plot item, right? And here's that business, right? Here's the example. Shape. We want to draw this thing as a ball. We can make color list, color options, color list. We can choose the color, and it's going to appear on the legend, the ones that are active, right? So there you go, the plot item drawing itself, and it's telling you 138 balls. If I say color by text value, so here we go. Let's say color by the ID number, and it's named. And so there you go. Since they're all unique ID numbers, they all get different colors, right? And you can turn them on and off over here. What else can you color by? Color by a numeric value, in this case, like ball radius. In this system, they all have the same radius, but there you go, ball radius, 0.09. And here's this vector quantity. So there's velocity. Now this is not the shape of an arrow. This is the shape of a ball. So now when we do a vector quantity as the shape of a ball, we have to do a contour. Okay, and so that's what this then is, right? And since it's a vector and we're just using a single color, it has to just be the magnitude or the x component or y component. So there you go. So you can see the high velocity, these two guys are still going high, right? So shape ball, color by 3 different types of things. Here's that. If you make the shape be an arrow for the velocity, now you're going to get this arrow plot, as we call it. Okay. Now let's go to the contacts. Here's your basic contact plot item, drawing it as a sphere. And then we're going to get these little dots. If you go into shape, you can control the size. You can always control the color with color opt. Here we go, 289. And by default, it's only showing you the active ones. Here we're just drawing it as a cylinder instead of a little dot. And here's the concept of all contacts, right? So look, if I go back, page up, notice 289 contacts. If I do the active ones also, now it's 347. Okay, so we're getting these, like say right there, there's no active contact, but, well, that's not one. Where is one that's doing this? Like say right here. It's not active, but it exists. So when I show them all, now I can see them all. Okay. Now we're coloring it by the type of contact model, the name of it, right? So here we go. And I'm still got all contacts active, right? So I'm coloring. They're all linear model, but some of them are active and some of them are inactive, right? Okay. Here's contact type. Is it a ball-ball contact? Is it a ball facet contact? So again, now we're just showing those as cylinders. Here, I turned off the colors of the ball, so here now I'm just seeing the ball facet ones, right? Here, oh no, this is the contact type. And here what I did is I turned off the other ones with color opt, so I'm only looking at the ball facet ones with the walls, right? What's this one? Numeric value. There's again the example, cylinders, Kn. Now I'm no longer using all contacts. Again, we don't usually care about that because it's not actually carrying a force. So there we go, Kn in this model, they're all the same. Here's this business about making a force chain. It has to be cylinder, force chain, and these both have to be checked. You can also look at a force chain plot in a different way. And what you can do, instead of just using 2 colors for compression and tension, which is what a basic force chain plot tells you, you can make the same image with the same thicknesses and orientations, but they're going to be colored now. The color is going to correspond to the magnitude. So it's going to look like this. Are you guys still there? I just heard something happening in the background. Are you guys still there?
Yes, we are here.
Yeah, okay, good. So again, notice if you switch between these, they have the exact same orientation and thickness, but now they're telling you magnitude by color. So the thicker ones, giving you the magnitude. And this is what you have to do here. Now you're going to have to choose vector quantity force, and then say scale by force and directed. Okay. The manual, here we go. This goes all the way back to 1979, the Kundal and Strack paper, ball and true ball. Here you go. This was the manual before PFC. And then we used to print these manuals, these big 3-ring binders. And then we got fancy and we started printing volumes like this. And then, as you know, after 2008, we have the modern world where we have these PDF files, and now we don't even have that. We have them embedded in the code, right? Mention a couple things. The Itasca software, there's more than just PFC. There's FLAC3D, there's 3DEC. And so it's all the same manual. And so some of the functionality is common to all of the codes. And so that is under here, Itasca software guide, not PFC. It's common. So an example of that is Itasca software guide, drill in there, user interface. And so this is talking about all the different aspects of the user interface. Okay. And Here's another in that common Itasca software guide. These are different commands and that are going to do like the domain. There's a domain in the other codes too, right? Like the history logic, okay? Like the plotting, okay? So if you know about PFC, you can easily use the other codes as well because they're going to look and feel and have the same interface. Now we go into PFC. Here's the outer level world. We go into the objects of PFC, right? All the commands are grouped by the type of object. So you've got the particles here, the walls, and then contacts have their own section. Each one of these objects has commands and fish functions, right? And again, the first word of the command is the type of object. So it's ball create. And the first word of the fish function is ball dot. Okay. As we've discussed, there's the PFC command genie because it's a command-driven program, right? And the way you do this is you very rarely type commands directly. You put them in a data file and then you call the data file. Every command is documented, right? So you can go in there for the balls. Here's the ball create command. This is what it looks like. It'll tell you the syntax. It'll give you a short description of what the command does, et cetera, right? For most things, for most commands, there's also fish function. So this is a way to create a ball with a fish function. So inside of a function that you're executing, you can tell it to create a ball instead of giving a command, for example. And then there's examples of all sorts of things to help teach you about how to use PFC. Obviously, the vast majority of people use PFC and they don't take a course like this, right? I'm always amazed that, you know, they just read the manual and they write journal papers, and sometimes they even do things that I had never even dreamed of, because this is such a very general code, right? You can do all sorts of clever things. You're really only limited by the sort of ideas you have of the algorithms of how you want to do this. And so here's an example. If you go to tutorials, there's balls in a box. This is where you're going to find it. So in PFC, up here it says help and documentation, examples, boom, down there. And here's this list, right? So I could say balls in a box, and it's actually going to fire up a whole new PFC, and it's going to open the balls in a box project, and it's going to open the tutorial description in the manual. Okay, so here's that new PFC, and here's that data file. And so I run it, and I can look at the plot, and I can see, you know, stuff like this. But then I can read about it, right? This is the useful thing. Here's that balls in a box data file, right? And then it's talking about stuff. So basically, you know, you can go through the, you know, and you actually should. You should like look through the manual, and it will tell you all kinds of things about PFC, and you'll learn how to use it. And the vast majority of people learn how to use PFC because they look at the manual. Okay. Think that's it. Yeah, for the user interface. Any questions about the stuff? Simple, obvious. Yes, no, good, bad.
No,
Yes.
good.
Good. Okay.
Okay.
User interface. Let's talk about these fundamental logics that are part of built into PFC that we use. We're going to just walk through them so you know what they are, and there's going to be some simple examples here. So let's go to that. So, and there's also a project in here. So you can open the project and you can follow along with the slides as we do this, right? So here's I say this as a framework because the code, there's a giant amount of code that we use to build PFC that's exactly the same as the code that's used to build FLAC3D, for example, right? And so we call that the framework. And this is the stuff that's provided to all the codes. So there we go. Look, I see PFC everywhere. So I use this word logics. It's not a real English word, but I kind of like it. It's fundamental capabilities. They have nothing to do with a discrete element model, but they have everything to do with being able to work with the model and do all kinds of useful things, right? So that involves the command processor, right? So you're sending commands to it. There's this history logic you've been using. There's this idea of XY pairs that are tables that we can visualize. There's going to be this range logic that's going to allow us to control when you give a command, you might only want it to apply to a restricted set of things, to a range of things. There's something we have not talked about, which is called the group logic. Every single PFC component, for example, every single ball can basically have a little mark in it that says, I'm part of group sand, and I'm also part of group clay. Well, not, I'm part of group sand, I'm part of group Fred, I'm part of group George. And then we're going to be able to give commands that only apply to certain groups. And we're going to be able to visualize only certain groups at a time. And we'll show examples of that. There's this measurement logic that we just barely sort of talked about. You remember that measurement circle? And we used it to get porosity. We can also get stress, for example. And then there's these things called extra variables. And the idea is very powerful and very simple, is that every object in PFC, like a ball, you can associate a fish variable with each one. And a fish variable, as you'll find out, is a general thing. It can be a vector, it can be a scalar, it can be a string that says, my name is Fred. And so every single ball, you can just make up your own fish variable and store it there. So you might have, like, you're doing a crazy model with a magnetic field, and PFC doesn't kind of know about magnetic fields, but you could implement a fish function to provide a magnetic field behavior. And so you might want to store like dipole, which I think is a vector, and you want to have the value of the dipole for every single ball. So you could create an extra variable and associate it with every ball, and in there you could store the dipole. So you have this completely general capability to associate information, data, with every PFC type of object: balls, walls, rigid blocks, contacts. Okay, that's the overview. So again, command processor, right? It's very general. I can put 2.0 for a floating point number. I can just do 2. I can put commas in here. I can put grouping things in here. It doesn't care. These are all the same command. This is a semicolon is a comment. So it'll process the line until it reaches this. Then it says, I'm done. I ignore that. So it treats it as a comment. Okay. We've mentioned this before. The commands are associated with the PFC objects. And this is a useful one. You can ask the command processor what it's expecting. So I can say ball attribute velocity question mark, and it's saying, oh, I'm expecting you to give me the value of the porosity. Okay, here's a better one. I'm running this logics overview, and here's my model, and I can say, I don't know, ball list question mark. Ooh, I can say any of these: ball list attribute, ball list contact, etc. Okay, so this question mark is a quite useful thing. And this business about bringing up the manual is extremely helpful, right? Just to make that clear. Here's my data file. What's the ball distribute command do? I put the cursor at the beginning of ball, and I think I hit F1. Or I just hit F1. And now here we go. That's the ball distribute command. Okay. Okay. So fire up PFC, and essentially we've done all this stuff, right? So this data file, my first pack. I fired it up. I executed it. And now we're going to look at things. This gives us a little simple model to illustrate ideas with. So there you go. That's my model, 686 cycles. And this one's not gravity. This one is actually walls, and there's enough particles in here that they're packed in there. So they're all in contact, and here's the force chains. Okay. So there you go, 138 balls, and this is how many contacts have force in them. So history, it's going to allow you to record a scalar value, and it's going to keep this. It's going to know this internally. It's going to store all that information, and it's going to let you plot them. It's also going to let you dump them out to text files. Okay. And it'll also let you dump them out to PFC tables, which are XYZ plots that you can then plot so on the screen in different ways. And so you might have 16 histories being sampled, and the one limitation here is that they're all sampled at the same rate. So every 16 PFC steps, it samples the values, and you can tell it what that is, okay, what that rate should be. It's typically 20 by default. Okay. So here's the example of using the history logic. So let's actually walk through this thing, okay? What we're going to do is we're going to take this model, okay, at this state, and we're going to delete particles up top, and we're going to let the thing settle, and then we're going to take this top wall and we're going to slowly push it into the particles. Okay. And so we're going to push down on the sand pile and record the platen force versus displacement. So let's just run the first part of that thing. So here's my logics overview. My first pack, start over, run it, and it saves my first pack. .p2 save. There it is. And it's a save file. It's sitting over here in the saved states. So I can double click it, and now that's the model that I have loaded into PFC. So this one, I always give the name of the data file down here. So it's called compressme.p2dat. I'm also have my own naming convention. So if it's a data file, if it's a bunch of scripting stuff, I would say .p2dat because it means it's going to be a data file that's going to work with PFC2D. And similarly, I'm going to do that when I make the save files. I'm going to say my first pack .p2 SAV. Okay. So compress me. So file on the upper left, open. It goes to the directory it's currently in, and it shows you the files. And I want to do compress me. So I select it, double click it, and loaded it in to the editor. And notice data files. I can double click on my first pack, and now that's what's in the editor window. I can double click this. Here's this one. So I'm going to restore my first pack. I'm going to change the title. I'm going to pause. After I pause, I'm going to delete the balls in the top, turn on gravity, and let them settle into a sand pile. So let's just run it up to that point. So here we go. Haven't cycled yet. I'm going to just magically delete balls up here, and then I'm going to run it and let it settle, just like we've been doing. Boom, pushes up, and I'm doing the solve ratio average, 1e minus 5. There we go, right? Simple enough. Compress me, just look at it again, right? Delete the particles, and cycle. Nothing else. So that's my starting point. I'm going to call that a sand pile. Then, so I'm going to restore that. Going to change the title, push down on the sand pile, record force displacement. So let's look here. Now we're caught up. This is what we're doing, right? So first of all, I'm simply going to make the top wall behave like a platen. So this top wall has a name, material vessel top. And I'm going to say, give it a velocity in the y direction of this value, negative. I want it to move down. And I'm using the range logic, which is going to allow me to say I only want to set the velocity of this wall, the one that's called material vessel top. Then I'm going to cycle. So I'm just going to let that thing move. I'm going to watch what happens. Yeah, I'm going to cycle here because I just want to get it close before it's touching. And I just screwed around with this so it would just get close. Okay. Now I want to start monitoring the, well, I'm going to slow it down first of all. So it's more of a slow loading. I just want to go really fast to get it near the top. Then I'm going to slow it down. Then with every object in PFC, we can monitor its displacement. Displacement means, by definition, the amount of motion relative to a starting value. So displacement is, you have this idea of every element you could say, oh, the displacement, I'm going to set all the values to 0. And then as the simulation proceeds, it's going to simply keep taking the velocity times delta t, which is the increment of displacement, and it's going to add that to that. And so notice I'm saying, first I'm setting of all the walls, I'm setting the displacement. It's a vector. I'm setting them all to 0. And it's just for that top wall. And then I'm going to monitor 2 histories, right? The total force in the y direction on that wall and the y displacement of that wall. Okay, and I'm going to give these names, force delta. And then I'm going to hook it in. Here's I go to chart, history chart, new plot item, select it, attributes, histories, click on force. And now this time versus, not just step number, but versus the thing I call delta. So it's now going to be monitoring, it's going to be plotting the force versus the displacement, where force and displacement are these histories. Okay, histories of that. And I'm not using fish here because the wall history command knows about, I can ask it to take these things. It knows about its force and it knows about its displacement. Okay. And so now I start cycling and I just watch what's happening. And here's my force, and notice it says history, force versus, and it's minus delta because I want to make this thing, I want this to be positive, so it goes up like this. Okay, so let's just run that thing. First, let's just run it. Here we go. Continue. Boom. We're getting that sand pile. Here we go. Now we're going to move that wall down fast and then hook on the histories. Notice it's moving fast for 2,200 steps. And now I make it move slow and I'm pushing, right? And I'm going to go for 2,500 steps. And now I want to make that history plot. First of all, history list. Those are the current histories being sampled, force and delta. That all looks good. Go over here to the plot plus history chart down here, history chart. Turn off the distracting things, select history. There we go, force delta. So force, so there we go. It's plotting the force. And it's a positive number because I asked for the y force acting on wall 3. So the balls are pushing in the positive y direction. That's the orientation. And by default, this is step number, right? So it's going from step number about 5,000, which is what it was when we started, up to 7,461. But I want to say VS versus. So I select it and I type in delta, the name of that, boom. Now it's still plotting force, but now it's plotting versus delta. but this is the y displacement of the top wall. So that's negative. It's getting more and more negative. And so the plot is actually this. It's going this way here. So I want to reverse the x-axis. So in here, I can say reverse. See, it says verse delta, and I can click reverse. So now I've got force, and when I plot the reverse delta, this is my force displacement, right? And that's what I have here. Force, displacement, right? Let's go. Change the axis so it has the right name. Let's make it red. And let's make this one start at 0, because that's kind of what I typically would want to see. And that, because I'm thinking of this as the force on the platen, right? Notice it's 0 to begin with, and then it comes in contact. And now it starts loading up. So how do I do that? History, what are the attributes? X-axis. Let's call it platen displacement in meters. There it is. The Y, what did I call that thing? Platen force. Newtons. And then notice it's not starting at 0. And so let's make the x-axis, it says minimum maximum. Instead of auto, make the minimum 0. Now this is my force displacement curve. And let's change the color. So here we go, series, force, and there's line, color. And let's make it red so I can see it better. And I can plot it as a line, or I can plot it as little X's. I can do all kinds of different things. Okay. And of course, if I continue to, and I can also plot this on top, right? And so here we go, we're watching what's happening, right? And of course I can continue to cycle, and the wall has a velocity, so I just keep moving it at that velocity, and you can see how the force is building up. And as it rearranges, it does all kinds of crazy stuff to do this. It rearranged into a denser state, so the slope is bigger, it's stiffer. Notice the slope of this curve is the stiffness of the material. And now it's not really rearranging much, so now it has a constant slope. Stiffness is the more contacts, the stiffer, the lower the porosity, the stiffer it's going to be. And as the contacts don't change anymore, this packing now has a certain stiffness, and that's why it's, so basically this is as it begins to load, it gets stiffer as more and more contacts form until now it gets to a state where there can't be more contacts forming, and it just keeps going up. All right? You with me? Make sense?
Yes.
What's going to happen if I, yeah, go ahead. Question? Okay. What's going to happen if I don't stop this wall? Starting to not make a lot of sense right now, this model. I got ridiculously big overlaps. So the physics, our assumption really for this physics to make a lot of sense is the overlap should maybe be 5 or 10% of the radiuses. It's still all in equilibrium and everything, but it gets to be kind of weird. What do we mean when you got these two particles with this giant overlap here, right? And in particular, we're going to start having these guys, they're going to keep getting bigger overlap, right? And as the there's no choice. There's only this much room, so they have to start overlapping. The stiffness times the overlap is the force. More overlap, more force. That's why the force keeps getting bigger. So this guy here, there's a force and an overlap based on the stiffness, and it's just going to keep slowly making it bigger. And in the world of PFC, we have to decide, once this centroid reaches the wall, what are we going to do? Because the fundamental assumption about how to get a contact between two objects breaks down. And so what we decide to do is once that happens, we remove the contact. It just disappears, which means there's a giant force right now pushing this guy towards the wall. It's all resisted by this contact. If we remove the contact, this guy goes really fast, shooting out of there. Okay. And so we can watch that happen. We just keep going. Eventually, the centroid's going to reach the wall and it's going to shoot out. Simulation's happy. There you go. Did you see that one on top? Look at how thick those force chains are. The force is giant. Also, every time one guy shoots out, it perturbs the total force on the platen. That's why that guy shot out, the force dropped, but then it continued to push. Force got back up again, right? So this is what's going to happen. If you're running a PFC model and you're getting particles that are going through the walls, that means something is physically not making sense. Like you may have, if your stiffnesses are much too low for your system, like you let it settle under gravity, there should be a certain force under there. If your stiffness is too low, the overlap will be too big and the particles will end up going through the walls, okay? If you set realistic properties for these systems, this will not happen. Okay, but here we go. Watch out. It's just going to keep on going forever, and eventually they're all going to push out, right? And we got these crazy overlaps, okay? Everybody good? Make sense?
Yes.
Yes.
Yeah, makes sense.
So you should
Yeah.
definitely, I've given this a lot of thought to try to come up with something to teach you. If you go over this stuff yourself, you should get a really good feel, do this, like start from scratch, make sure you can make this history and look at, make sure you can reproduce this thing here, okay? We just have 10 minutes. It's basically an index set of XY pairs, right? We can plot them with the table plot item. And there's all kinds of things this is useful for. So for example, I did a bunch of work in FLAC3D to have shell structures. So here's a shell structure with pressure on the top, loaded with sitting on the two sides, can't move. So it's the bending, right? And this is the deflection at the center. And so we're plotting deflection versus step number. And eventually after the pressure, it equalizes, you get the displacement is, the deflection stays the same. And so we can then we can use the table logic. We can walk across this thing, get the displacement at every point, throw it into a table, get the deflection, throw it into a table, boom, boom, boom. This is the distance across. With a fish function now, I can build up this table and I can display it. And then I can write a fish function that tells me the analytical solution, which is the black thing. And now I can put both of those in there and I can like compare them, right? So here's the analytical solution in black. Here's the PFC or the model, in this case, FLAC3D. But this is the example. These are very powerful things. You don't have to do it in Excel. Okay, so you can really do a lot of, like research type stuff with new ideas and things by just working with PFC itself because of its logics. Here's now the important thing, range logic. So it's going to restrict the command to just a certain thing. It's like a filter. So ball delete. I only want to delete the balls whose x coordinate is between 0.5 and 1. So here's my model. This first pack one, the 0, 0 is down here. And this is 2, 2. So if I do position 0.5 to 1 in x, that's this region. And I said delete everybody in that region. So I give this command and suddenly those guys are deleted, right? And there's an example, right? Range it. There's many different, we call these range elements. The position, the ID. There's an annulus. There's for example, or a circle. So here, in the circle that has this radius and center, that's the range. So I want to delete the guys in that circle. Boom, circle, radius, 0.5, center, 1.21. Boom, all the guys with centroids in there got deleted, right? So that's my range. And you can combine these things. So here, for example, this is like Boolean logic, right? So everybody with x between 0.5 and 1, like before, and that's a circle. Look, boom, boom, it's Boolean logic. The ... that means it's one line. It's a line continuation. So this is one command, right? So there you go. So it's very, very generalized and very, very powerful. Here you say Boolean logic. So it's a not. It's not that part. So this is the inverse, right? Instead of this, it deleted the other part, the outside part of that. Okay. Okay. Makes sense? That's what I'm going to say. That's range. We use it all the time. Okay.
Yes.
Okay. Here's an important one, groups. So think of this as a group is simply a name, and you could, an object, a model object can have a whole bunch of group names associated with it. Okay. So here, for example, think of the group name. Think of this as here's all the data with a ball. Remember when we clicked on the ball, we got that giant box with all the different information about it. So one of that information can be these, think of these as little sticky notes with names on them. So this ball data now, this ball has, we call this a default slot. We think of these as slots that have names. So there's a default slot. So I'm going to say, I want to have that name be left side. It's part of the group called left side. So how do I do that? Ball group left side. And now I'm using the range. So this command, ball group left side, is only going to apply to the guys between 0.5 and 1. So there you go. All balls in that region have the name left side. So now I can have the ball plot item knows how to color by group. It's a text value group. Remember, groups are just names. So there you go. Ball text value group. There's two possibilities. It's either none or it's the default slot called left side. Right? And then now I'm seeing those guys. And we can have multiple ones. So here, for example, instead of just using the default, we're going to say there's a slot in here. It's the layer slot. And so I'm going to say, oh, the layer is deep and the material is clay. So here we go. The group deep, that's the name I want to put there. And I want to put it in a slot called layer. Okay. So now I can say ball text value group slot is layer. So now it's going to say, oh, the layer group. These are the guys that are deep that have the word deep. These are not, these are none. These are the guys that are clay, and these are the none. Oh, and these are the guys that are both. That's what this is telling me, right? Layer, deep. So these guys here are have the word deep in their layer slot and have the word clay in their material slot, right? Okay. And you can turn this on and off and everything. So this is like the most powerful thing. This is how we're going to associate different stuff, right? Give layers of a material. These are the balls that are layer 6. These are balls that are layer thread. Okay. Measurement logic. We can measure different quantities. These are macroscopic quantities, right? Like particle size distribution. We didn't do that. We used a function, but you can also do it with a measurement circle. Coordination number is the average number of contacts each particle has. The bigger that is, the more contacts each particle has, the sort of less porous it is, the more strong it is. That tells us a lot about the system. We can also measure a stress tensor, which is kind of weird because we don't have stress here. We just have force. But you have force chains. And so if you think about it, you can work out the mathematics that says I can essentially integrate those force chains and I can come up with an equivalent stress tensor. And that's what PFC will do. And I can also come up with a strain rate tensor, which basically characterizing the strain rate, which is the change of strain with time. And then if we integrate that with delta t, we keep multiplying it, we get a strain. So this is a whole tensor quantity, okay? So this is a way of taking this system. We're going to use this especially when it's a bonded system. We're going to build a specimen, bond it together, and say that's a sandstone, that's a rock. And then we're going to use the measurement logic to say what's the stress in this part of the sand. And then we're going to use this logic to say what's the strain that's being applied to it. Okay, so we've gone from a bunch of particle information to an integrated concept of stress and strain here. Okay. And there it is, measure plot item. This is like what we did before, right? And this is exactly what we did before, measure porosity. Okay, we'll fix this bug soon. The last thing, and then we'll be done, is this extra business. So again, you can associate information with these extra variables, and they can be plotted and accessed with fish. So here, for example, here's a command. I want to associate with every ball an extra variable, and there can be, they're numbered, so there can be 128 different extra variables. So extra variable number 1 is going to be a vector that has the value in it of 1, 1. And I'm only going to do make this extra data for the guys in this region. And then I can say ball shape is an arrow. It's a vector quantity, extra, index 1. Boom. It's drawing it as an arrow. And notice it's 1, 1. That's what I'm seeing. And they're all the same. And they're only those guys. So now I'm looking at that data. Okay. And then here, I'm using slot number 2 of the extra variable. And I'm going to give it a name, a string called cement. And so now I have to do shape of ball, but I want to color by extra 2, which is the cement. And so there we go. Those are the guys that have the word cement. It's a text value now. And that's the idea. So yeah, you should look at this. And now you have, this is kind of the bulk of everything about PFC except fish. And so I'll send you this stuff. If you have some time, it would be it would be useful. I guarantee it would be useful to go through this so you can do this stuff. And then we'll continue on. We'll actually finish out these examples where we turn it into an odometer test, right? And you can see this example, we pretty much created an odometer test right here. So that's what we'll do. We'll continue on. We'll talk about fish, and then we'll get to, in the lecture after that, we'll talk about bonded particle modeling. Okay? Any final thoughts?